Today we're going to discuss section 4.5. Section 4.5 is about the fundamental theorem of calculus. The fundamental, I stress the word fundamental, theorem of calculus. See, let me remind you a little bit what we've done in section 4.3 and 4.4, at least section 4.4. In section 4.4, we defined the definite integral from a to b of f of x dx to be the limit as n approaches infinity of delta x multiplied by the summation from I equal 1 to n of f of x I. Those we call them Riemannian sums, and we take the sum of the limit of the Riemann sums as n approaches infinity. If you remember, this gives us if you want to imagine, it gives us the total area under the graph, of course with some limitations, if the function is above the x-axis, and if the function is not above the x-axis, it alternates between above and below. It's the signed area in a certain sense, and we already understood how this works and everything. Now the sign of the integral, the definite integral here, resembles the indefinite integral that we have learned in section 4.1, which says the integral of f of x dx is, by definition, the antiderivative f of x, meaning that, which is equivalent to saying the derivative of f of x, this one, is equal to the function that we started with. So this is the antiderivative of this. So when we differentiate this, we get f of x. So the antiderivative of f is capital F. The derivative of capital F is small f. Many students think that by definition those are defined the same thing. No, this is how they are defined. These are the true definitions of both what we call a definite integral and what we call an indefinite integral. This assumption that they are the same thing is not true, but lucky us, a theorem, a very big theorem called the fundamental theorem of calculus, FTC. The fundamental theorem of calculus came, and this fundamental theorem of calculus said that, you know what, the antiderivative, a simple way of getting the antiderivative, a simple way of getting the definite integral from a to b of f of x dx is by finding an antiderivative f of f of x, evaluating it at the upper limit b, minus f evaluated at a. This is not the definition of this integral. This is a very big theorem, and because it's a very big theorem, they called it the fundamental, like it's the basis of all calculus, but it's a theorem, it was proven. These were the definitions, two separate definitions that have no relation whatsoever to each other, two separate definitions. The fundamental theorem of calculus came and linked those definitions together. So when you do the indefinite integral of f, you find capital F of x plus c. This capital F, you use it in definite integrals, so that the definite integral from a to b of f of x dx is this capital F of x evaluated at the upper limit first, it's very important, minus f evaluated at a, which is the lower limit. See, this is one of the parts of the fundamental theorem of calculus, and this is actually not part one, this is this is actually part one. Students relate a lot to this part because this is what they define definite integrals as in schools. They don't know that this is not the definition of the definite integral. They define it as such. This is only a method of calculation to simplify our lives. But by definition, what are definite integrals? They are limits of Riemannian sums. So it's a totally different idea. Of course, we do not go in the proof because it's a fundamental theorem of calculus. We do not really work with proofs and partitions and so on, so like. All we do is we just take it as if it's given to us. So integral from a to b of f of x dx is the antiderivative f evaluated at the upper limit b minus the antiderivative of f evaluated at the lower limit a. Now this is very easy to understand and very easy to apply. So now, for example, let me give you an example. Let's assume we wanted the antiderivative from minus 1, the definite integral from minus 1 to 3 of x squared plus 1 dx. All right, let's find it by using Riemann sums. The old method. It's like a revision for section 4.4. What do we do if we want to use Riemann sums? First, we get the width, delta x. It's b minus a over n, so 4 over n. Then second, we define right endpoints, which are xi's. Xi's are minus 1, which is a, the beginning of the interval, plus delta x times I, so 4i over n. Third, we find the function values of those right endpoints by applying the function on this. So we get minus 1 plus 4i over n, the whole thing squared, plus 1. Expanded, we get 1 minus 8i over n plus 16i squared over n squared plus 1. You simplify it, you get 2 minus 8i over n plus 16i squared over n squared. Fourth, you get the sums, the Riemann sums. What are the Riemann sums? They are delta x, never forget, they are areas of rectangles, so it's the width, 4 over n, multiplied by all the heights, the summation of the heights, because it's the sum of all the areas of those rectangles, if you remember the technique from section 4.3, which is the width multiplied by the height. The width is common, so we take it as a common factor. What is left is the sum of all the heights, so it's the sum from I equal 1 to n of all the heights, which are the function values. Delta x times summation of f of xi from I equal 1 to n. This is 4 over n, and we up in brackets because it has to multiply every single answer of those. And the answers of those, when it's a constant, the summation of a constant is 2 times n, minus 8 over n stays the summation of I, because the only variable here is I. 8 over n, 16 over n squared, they are constants. The only variable is I. The summation of I from 1 to n is n plus 1 over 2, plus 16 over n squared stays. Now the summation of I squared is n plus 1 to n plus 1 over 6, close the brackets. Now simplify this. No need to simplify anything and cancel, only multiply. 4 to n, 8n over n, minus 4, 8, 32, n plus 1 over n times 2, 2n squared, plus 4 times 16, 64, n plus 1 over 2n plus 1, all of it over n squared, 6n cubed. Now the fifth step is the integral that we're looking for will be the limit as n goes to infinity of all of those n's that we have over here, those 3 pieces, 3 parts. The limit of the first, of course, limits at infinity are highest power up, highest power down. 8n over n is nothing but 8, minus 32n squared over 2n squared, 16, plus 64n and 2n, it becomes 128n cubed over 6, so 128 over 6, because they have the same power, n cubed, n cubed. If the power up is bigger, that's infinity. If the power down is bigger, that's 0. So the total becomes minus 8. Let me calculate it. It's minus 8 plus 126 over 6. The full answer is 13. So that's the integral if we calculate it using Riemann sums, just to remind you of the technique of the definition of definite integrals. Now the same, I want to make sure that I get the same answer using the fundamental theorem of calculus. So over here on the side, I will put next to it, integral from minus 1 to 3 of x squared plus 1 dx, using now what? The fundamental theorem of calculus. What's an antiderivative of x squared? Powers, you add 1, divide by the new power, plus. What's an antiderivative of 1? X. Usually an antiderivative of this function, we will add to it c. But I will show you why the c is not important. That's why usually we omit it. Where will I evaluate this antiderivative? So I found this is capital F of x. This capital F of x needs to be evaluated at b, which is the upper limit, then evaluated at a, which is the lower limit. So now we substitute 3 to evaluate it. What do we get? 3 cubed, 27 divided by 3, 9, plus 3, plus c, minus, remember, f of b minus f at a. Minus 1 cubed is minus 1 over 3, minus 1 plus c again. Now what does this give us as a final answer? 9 plus 3, 12 plus c. Here we get minus 1 over 3. Minus 1 is minus 4 over 3. Did I do a mistake? I calculated 126 over 6 in the previous one. It's 128 over 6. The answer is 40 over 3 here. Sorry, calculation mistake. I put on the calculator 6 instead of 8. Yeah, because it didn't seem to rumble. So 12 plus c for the first bracket, minus 4 over 3 becomes plus 4 over 3, minus c. Do you see the c minus the c cancels? That's why usually we never use a c when we are doing definite integrals. We only use c when we are doing indefinite integrals. But for definite, indefinite integrals like those, we do not use it. So this is equal to how much? 12 plus 4 over 3 is 40 over 3. So do you see we get exactly the same answer using the two methods, 40 over 3 and 40 over 3. I used Riemann sums just to remind you of the definition. And now I use the simple strategy of the fundamental theorem of calculus part 1, which shows us that in order to get a definite integral from a to b, you only need to find an antiderivative of f of x, which we call capital F of x. You evaluate that capital F of x at b minus capital F at a. This will directly give you the answer. Notice answers of definite integrals are always numbers. You are always calculating numbers, unlike indefinite integrals. Indefinite integrals usually give me functions. All right, you are finding an antiderivative, you are giving me a function. But definite integrals, which have limits, their answers are numbers, constant numbers only. They do not involve any x's at all. All right, we'll be back.